Hi guys, today we're going to continue with nuclear magnetic resonance, and we're going to do this part here on splitting patterns. Right here, number of non-equivalent protons adjacent. The keyword is adjacent to a given proton. Adjacent means what? Let's say this is the proton here, this carbon here, right? This is another carbon here, another hydrogen here. And let's say this is the one here. All right, this is ethanol, easier. Right, now these three here are chemically equivalent because they got the same chemical environment, same type of neighbors. This hydrogen to carbon to carbon to hydrogen to carbon, carbon, oxygen, they're all same, is it? So now this is called the adjacent, it's called the adjacent. Okay, adjacent hydrogen to this one here, and this one here. Okay, this fellow here, and this fellow here. Okay, and I put the blue color here, right? So this and this are called what? Adjacent proton. Okay, non-equivalent. That means these two are not same as these three. Okay, these three are what? Equivalent. Okay, equivalent. Equivalent. This it is equivalent. Equivalent. But this and this are what? Non-equivalent. So now this non-equivalent means this one here, this hydrogen here, this hydrogen here, will affect this three fellows here. Okay, this and this fellow here. This is called adjacent. See here, proton adjacent to a given. So let's say this is the given. Okay. Now, how do I know that this is adjacent? There are three bonds here. 1, 2, 3. Bingo. So this one is adjacent to here. 1, 2, 3. Bingo. So these two are adjacent to this hydrogen here. Same thing. This one is 1, 2, 3. It means it's adjacent to here. Same thing here. It's 1, 2, 3 now. Okay. So these two fellows are adjacent to these three hydrogen. Okay. Okay. To a given proton from the splitting pattern. Okay. Using the n+1 rule. Right. So we're going to look at this today. After this one here, then we'll look at some of the questions, easy questions first, and this will finish up the whole video today. Okay. Right. And later, when I do the mass spectrometer and review over the infrared, we'll do the harder question. They all will combine. Okay. So our aim is this. Now let's look at how do we get this splitting patterns. Okay. Now let's look at page 24. All right, 24. Okay. Now remember the proton. This is the proton. Okay, nuclear magnetic resonance spectra of a organic compound gives 4 informations here. Okay, 4 informations. Okay, and one the type of signals. Also, number of signals. How many signals here? We should tell you how many different kinds of protons there are right now. For example, we did that there is CH3, CH2, and OH. In this case here, there are 3 kinds of protons. The CH3, which means it is in the furthest from the oxygen. That means it will be this. Right. Okay, this one here. Okay, so if it's CH3, it will be quite near 0.9 or 1. Okay, if it's CH2, that means next to a carbon, of course. If next to a carbon here, it'll be maybe 1 point something. Okay, right. And of course, so this one here. Remember, if it's CH3 and it's CH2 here and OH here. So this one here, CH3 will be around 1 point something, 1 point, 1.2 or whatever. Okay. Now these two hydrogens here, right, next to oxygen is here, where here. Okay. CH2 next to oxygen here, right. So 3 point something. If it's CH3 to oxygen here, it'll be lower. If next to a carbon here, got more pool electron here, more here. So about 3 point, maybe 3.5. Okay. Right. 3.5. This will be 3.5. Of course, OH here will be 0.5 to 6. So there will be 3 types of hydrogens. Okay, that's what it says here. Types of hydrogen. Intensity, of course, is measured. It tells us how many protons, how many is the types or kinds Okay, from the height you can say because it's 3 is to 2 is to 1. Okay, but the position of the signals also tell us about the electronic environment. It means what? It means next to the electronegative substance like here. Alright, this hydrogen is next to oxygen here. This one is further away. Right? Okay, now come to the next one here today is our today's our video. It's a splitting of a signal, one signal, into several peaks. Right? It tells of the neighbor, I told you, the neighbor hydrogen, which means the adjacent hydrogen. Okay? So now let's look at what it means first. Well, we'll take an example. Okay, look at page 35. I'm going to make it faster. 35. Okay, now this is the nuclear magnetic spectrum of propanol. That's what ethanol. Sorry. Okay, here you can see here. Well, sorry, here. I didn't say here, right? It's here. Okay, now this is low resolution. Okay, this is a high resolution of ethanol. See ethanol. Okay. Now, high resolution, low resolution. Now, this low resolution of ethanol. Let me just put a bit smaller. Okay. Now, what does it tell me? I'm going to put up here. Okay, here. Okay, I'm going to draw reverse so that you can see it clearer. Okay, C H here. I know you're new to this, but you need to practice it more. Okay, H here, this ethanol. Okay. So because these 3 hydrogens here are equivalent, chemically equivalent. Why? Because they have the same type of neighbors in. So these 3 will give you one signal. And where will this signal be? Of course, it will be this one here. 0.9 to 1.7. Because there's oxygen there, of course, it will be, well, a bit higher because oxygen here will withdraw electrons here. So it's about, let's say, 1.2. I put on here 1.2. Okay. So now this is low resolution. Okay, low resolution. Okay, right? That means you kind of see all the details, like low resolution television. Okay, okay. So now the height is highest here, and of course you see here, right here. I put it smaller. All right, better. Now this CH2, this H here, and this H here, because it's the carbon to oxygen. Okay. You can see here, carbon to oxygen here, 3.2 to 4. Okay, so here about 3.2 to 4, and 3.7 here. Okay, because next to oxygen, which is very electronegative, isn't it? So this is the low resolution. It says here, low resolution of ethanol. All right. So of course, this further up here because it's oxygen here. Is very electronegative, so it will pull electrons away. So this hydrogen will experience a very large external field. So it's about 5.5, let's say. Okay. Now this is low resolution. So what happens if you put a high resolution instrument? Okay, it will split this one into give you a clearer. This low resolution means this is the average. No, this because the average. You can see it's this requires 3 is to 2. So 1 yeah, because from formula can see it actually, right? You can measure the height, so it gives you the relative. Okay, now this is low resolution. Okay, now high resolution. Now this is high resolution. Now what does it mean? It means that now I'm going to show you actual question paper that asks you about this. Okay, I'll tell you why. Okay, page 56. They actually ask this thing 56. I'll show you a simple one first, okay? Because later we'll do the all mixed together with your mass spectrometer and your infrared. Now here, see, right? NMR spectroscopy give information about groups adjacent. Yeah, we use the word adjacent now. Adjacent groups of hydrogen. Actually means groups of hydrogen adjacent to a particular proton, a particular hydrogen. Okay, as well as about the proton itself. The process which gives us information about adjacent protons is called spin splitting or spin coupling. Using ethanol as an example, explain the spin splitting pattern associated with each of this group. Okay, now you see As I told you, these three fellows here, I'm going to make it a bit bigger if I can. Okay, remember we said that these three hydrogens here, HA, HA, and HA, they have the same chemical environment here. So of course, I'm going to draw the low resolution here. Okay. Right. Here is your 0 TMS. I told you here about this one. Well, let's not put this on here because I need to draw the OH. You all gone. Okay, never mind. You can do it again. Draw. Okay. Okay. This is 1, 2, 3, 4, 5, and 6. Okay, going down here. So higher this one. Okay, 2, 3, 4, 5, and 6. Now this is all parts per million. Okay, the chemical shift. Now TMS is 0 here. Now the first, of course, if you look at this part here, it's about 1.2. This one will give you 1.2. Okay. So now this low resolution. Okay, low resolution chip TV. Okay. So let's say here 1.2. Right. 1.2. Okay. Let's say this is the peak here. Okay. So it goes up here and go down. Okay. And of course, the other one is I forgot what we are. Let me just check again. Okay. Patient by 2035, 635. Okay. Right. So it's what? 3.7 and 5.5 now. Okay. 3.7, 3.7 and 5.5. Let me just go back to the other one here. 56. 3.7 and 5.5. 56. Okay. 3.5. 5.5, sorry, 3.6, 5.5, and 3.6 over here. Okay, this 2.6. So this is this belongs to the CH3. Okay, of course here, 2, and 1 here, still. Okay, so this one will show the CH2. This one is the OH. Yes, not. Now, under high resolution, we'll draw like that. Here's your TMS, which means I can see clearer. It's not here. Okay. Now this one belongs to this one here. These three fellows here, right? Will give you the reading of 1.2. Okay. Right now, you see, when there's an external field here, okay. HO or BO, up to you. Let's go HO, okay? Right now, okay? The field here. Now, it's affected by protons adjacent to this HA. Adjacent means what? 3 bonds there. So 1, 2, 3. That means this fellow here. Okay, I'm going to put blue, red. Red. Okay? That means this fellow here and this fellow here. Both of them are adjacent to this end. Why? Because the 3 bonds, this is adjacent. Adjacent. Okay? This HB is adjacent to HA. Right? Now, I'm talking about HA, yeah? HA here. So HA here, that's 1, 2, 3. Yeah? Okay? Now this one, yes. That means this one will affect this one here. This one here, 1, 2, 3. Yes, not. Same here, it's right here. 1, 2, 3. Right? 3 years. So these two fellows here will affect this peak here, this main peak here. This one peak here. How will it affect it? Remember these 3 fellows here will give you this peak here because of the external. It's the external what? External magnetic field. Yes, not. Okay. Now, this proton here and here will also have a small. Can also be spinning up or down. So there's a small field going up or going down. Or going down. So can be going up or going down. Yeah. So this 2 adjacent hydrogen because it's near, right? Now, if 4 cannot, 1, 2, 3, 4. This HC cannot because there are 4 bonds here. You put the H here. It's 1, 2, 3, 4, and anything that's oxygen separated, it won't. Like here, so this H will not affect this 2H. Yeah. Okay. So oxygen here will separate them. Okay. So here, this 2 HP, right? So now, how they say it here is the HA, the 3HA here, right? HA here, right? Can see is affected by these 2 HP. Now HP and HP, okay, HP, yeah, right? For HP, how many ways it can spin? For the first one here, 2 one here, it can spin up and up, up and up. Okay, that means up and up. That means up. If it spin up and up, the external field is HO. That means it's HO plus this 2, isn't it? So plus 2 here. That means this fellow here, the HA, will fill HO plus 2, isn't it? A small amount, okay? Which means it will actually have a higher field, isn't it? Higher here. Yeah. So it will here. So it's 1 here, and now this is 2. So okay, now this is the low resolution. So it will have it will fill somewhere down here, maybe 1 point. Now if this is 1.2, it will fill 1.25, a bit lah. Okay, so so now, so the possibility is up. Now what's the possibility? It goes up, and that one go down, isn't it? Okay, right. This goes up, right, and this one go down. Okay, go down. Rub it off first. Rub off here first. So remember, okay. Okay. Now the first one is it goes up and up. Okay, right. So up. That means this 3 fellows here will fill 2 of them going up. That means HP plus 2 of them, so plus 2. Now the next possibility is that it goes up and then go down. Okay, so go up and down. Of course, that means they cancel each other. That means it's 0 effect on the whole thing. Okay, or this one goes down and this one goes up. Okay, so down and up. And this one is 0. Of course, they cancel each other. The last one will be down and down. This one. Okay, down and down means minus 2. That means minus 2 means it's going against this field. It's going down here. It's going down here. So against the field, it means that you will feel less of the field. Right? That means you got more electron density. That means it will be up from here. So there's another one here. Here, 1.9, 1.1, 1.15. Okay, right, lower. Right now, there's one possibility here. 1 plus 1 is 2 possibilities here. Okay, the 2 chances here and this one. So it will split. So this fellow here, right? This fellow here, this HP here, will split this one thing here into 3 bits. Okay, because the 2 chances of here, one here, so it's 3 chances up here, and 1 here, 3. Okay, so that. Okay, 3. Right. So you can see later. Okay, so here. Right. So this how they explain. Okay, now let's see how they explain 04 number. All right. Now first of all, they ask you the question. Let me look at the question first. Right. Now, nuclear magnetic resonance give information about adjacent halogens here, the particular adjacent as well as the process. So using ethanol as an example, explain the splitting patterns associated with each. Now, see, I'm giving examples, explain the splitting patterns. See, the mark is 5 marks. Now. It means you will explain them from the very beginning. See, my first mark. Each proton magnetic field. The first one, of course, each proton magnetic field. See, you must know what Cambridge wants. What they want, you must give. Each proton. Now, remember, there are 3 kinds of protons here. Oh, a bit smaller. Okay. Right. Yeah. Okay. Now look at it here first. Let me explain the answer so you can get a clearer picture of what Cambridge is trying to tell you. Now, each proton magnetic field, that means each of them here, HA, and HA, right now, and HB, Hb and this Hc. Each proton, each type of proton, and every proton here, right, its magnetic moment is can align with, let's say this external field, okay, BOHO, okay. That means this one can go up, 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 and up, okay, or can go down, up and down, or can go down, down, and up, okay. That means if they align, can go align with or against, right? There are only two choices for every hydrogen, okay. And because of this, it gives every proton here can give up to two energy states, right? Because remember, when there is a magnetic field, they will split them in two parts, okay, right? Okay, and of course, the flip from here to here, right? You absorb the energy, okay, and this the frequency here equals to, well, H frequency. The frequency is measured according to your parts per million or your temperature. Yep. Now, okay, so 1 mark is for each proton magnetic moments align with or against the field is 1 mark. Actually, this is the principles of NMR, okay? And this will give rise to two energy states, right? And of course, the third one, of course, if you talk about principles, I think it's one principle here. Okay, one principle here, okay? See? Now, this is on the marking scheme for principle. Each proton possesses a nuclear flame, right? And the nuclear spin here can align with, say, this generated magnetic field. See, this is 1 mark each, no? This on the, later I'll show you, okay, but don't have time. They ask you, now this is on the, what is this called? This is called the principles. Principles of NMR. Put it smaller, okay? So the first principle the mark is given is each proton possesses a nuclear spin. Right now, spin up or spin down, clockwise or anti-clockwise. This is the first mark. And because of spinning here, right, they will generate what? A magnetic field, right? Up or against, okay, right now, okay? The second mark, okay? So the moment can align with or against. This is the same thing, but give a mark here. Align with, okay, magnetic field can align with or against magnetic field. So if align with the field is high energy, so align with the field is low energy, align against it high energy. So give it two energies now. 4 marks now. 1, 2, 3, 4. These are the principles of NMR, which I'll talk later, okay? Right? And of course, you talk about splitting here, right? The external field can be modified, can be changed by moments. What is moments? Magnetic field. From other protons, which means other adjacent protons. Adjacent protons. Adjacent protons. That means the proton, that means like here, right, like here, okay? Right? This is the adjacent proton to this one here. Why? Because 1, 2, 3 bond. 1, 2, 3 bond. That means these two will affect this one here. These two will affect this one here. These two will affect this one here. That means the magnetic field of these three fellows here can be modified by these two guys. See now? Okay? Right. And of course it says here 1, 2, 1. Right? So these two fellows here will change this one peak here under this 1.2, right, to 3 peaks. Okay? So here's 1.2 here. Of course, lower a bit. Now this here will be 1.25. Here we what? Here's 1.15. So it's 1 peak here, higher here, and here. There are 3 peaks here. This is 1, 2, 1. Now this is called splitting. Understand? Okay, now let's go on here. Right. So now they say, now remember this fellow here, right? See, it comes up twice, for your ethanol. This fellow here, the neighbor. Why I talk about this three first? Because it's the one that's the lowest one here. Okay? This three, isn't it? Will be split by these two fellows here. Now, how did this fellow answer? How did they answer here? You see, right? Okay. See, each for a given proton, let's say HA. Okay, HA. These are 3 same not. HA. C is that means tengok lah. It means it's C is 2 fellows here. Okay. It means 1, 2, 3. No. Number 1, 1, 2, 3. Number 2. That means these 3 protons actually see these 2 fellows here. Okay. For given proton sees adjacent protons and say that means this guy here will see B. and B here. Now, what does it see? It will see that HB here, HB can have, first of all, what are the spins that HB can have? Okay, can spin up and up. Okay, that means both are spin up and spin up. Okay, now these are the possibilities. Okay, right now. And of course, you can see this one can spin up. This of course plus 2, right? Because it's going to be with the field. HB, HO. Or this fellow here can spin up, and this one can spin up, and this one can spin down. Spin down. In this case here, if it sees this energy state, this spin state, that means it doesn't affect it because it cancels off each other. See, right? And of course, it can also spin down and spin up, right? Which again is 0, right? It cancels off each other. Okay, so this one will not affect the magnetic field that this HA will feel. But of course, if this one spin down and spin down, okay, down, down, that means both will be against the field here, so -2. Right? That means this fellows here will feel less of the external field, right? That means feel less, right? No, sorry, feel more, right? Pull down, sorry, feel less, right? Right? Because it against the field here, so it split less. So it's here, HA, this one here, I put red color, HA, red color, okay, HA will, right, HA, right here, HA, proton, will see 2 HB, this one here, this one here, okay, and we'll give rise to a triplet. Why? Because these two are same energy. Okay. That's not okay. So one will be higher field, one will be low field. Means this is 1 is to 2 states in 2 is to 1. So you see, give a triplet of 1 to 1. Now HB. Okay, HB now. So HB. These two fillers here. I told you oxygen here separated. This one won't affect anybody. Okay, because oxygen is 2 electronegative, so it separates everything. Okay? It will block the field by H here. Okay, so now these two fields, these 3 fellows here, because why? Adjacent. 1, 2, 3. That means now HA is adjacent proton to who? This HA is to HB, is it? They will affect each other. So of course this HB and this HB will see 3 of this fellow here. These 3 are actually 1, 2, 3, 1, 2, 3, right here 1, 2, 3, 1, 2, 3, 1, 2, 3. So these 2 will see these 3 fellows here, and these 3 fellows here can also have spins. Okay, so what kind of spins can they have? Okay, now let's see here. Okay, of course it can spin up. So it can spin up, spin up, spin up. Okay, the first. That's the first possibility, okay? Spin up, up, and up, +3. That means the HO plus 3 of them, that means the extra field. That means it will feel a bit higher than the normal one, okay? Now, of course, it can spin up, up, and down. The possibility is there. So spin up, up, and down. So these 2 cancel out, that means +1. So you feel a lesser field than this one here, right? Or it can spin up, down, and up, which is also +1, isn't it? So same, right? Not? Yes. Or it can spin what? Down, up, and up. So there are 3 poles here. Yes. Sorry, here's +1. +1. Okay. So it's +1 as well. Okay. Right. So here. Okay, 3. Right. So now this 3 is +1, isn't it? See? That's why it's a triplet. This 3 here. This one is 1 here. Now next one is spin down, down, and up. Okay. Right. This one is, in this case here, is -1. Whereas this one cancels off. This one is spin down, isn't it? Or here up, down, and down. Right. -1. Or down, up, and down, also -1. So these 3 are same, isn't it? Right? So it will be upfield, downfield, sorry, less, it feels less. So this will be, this is +1, this +3 is -1. Okay. The last one, of course, it is all will be spin down. So it's -3. See? So this is one possibility. So this one possibility. So it's 3 possibilities. This is 3 possibilities. This one possibility. So that means this, right? This 3 fellas, means the HB will split. So HA, sorry. HA will split the HB into 4. See? So 3 will split into 4. It means it's called the multiplicity law. N is the number of hydrogens plus 1. Yeah. So the HB will split into 4. 1, 2, 3, 4. Like that. 1, 3, 3, and 1. Okay. The original one is somewhere in the middle. Okay. Okay. So here. So if a low resolution, it will be like that. Like that. Okay. So it will not see, it's not very clear. So high resolution, we can see clearer. There are 4 peaks here. And these 4 peaks here is for HB. Right? Split by who? Actually, there are only two hydrogens here. It's split by the 3 HA. Okay? That's why HB sees 3 HAs, giving 1, 3, 3, 1. You can draw all these fellows here in your exams, okay, to show that you understood, okay, the possibilities of spins of the neighbors. HC, so here C is not just neighbor, okay, so it's a singlet, okay, right? Because oxygen blocks it. Clear? Now let's go back to, now this is how they answer the the HA sees HB. Sees how many HB? Sees 2 HBs. So it's split into 3, into the 3 peaks, or triplet 1, 2, 1. HB sees 3 HAs. So it's split into 1, 3, 3, 1, a quartet. Okay, now this is called the multiplicity law. You don't understand, go back again to the video and see again what I say. Okay, I won't go to again because it's time consuming. Right? So you can see here. Right now, I'm going to go to the theory again here. It's in page 4. You can see. So I discussed in terms of past year questions. Sorry, here be 35. 35. Okay. See now. So this low resolution. So this is a CH. This further here was split by the CH2 here. So I told you here. I do it again now. Right. So remember this fellows here, these 3 fellows here, or we call it HA. A here. We'll see this HB. We'll see how many HB? 2 HBs. We'll see what? See their spins in, or see the energy levels in. So the HB can have how many different kind of spin? Well, if it spin up and up, so if up and up, that means it's going to be with the field. That means it's going to be higher there. So this one will be a bit higher here. One here, just a little bit higher. Okay. Okay. Then of course these 2 fellows here can be one going up. Now this is +2. One going up, one going down. It's cancel off. It's 0 here. Or one going down, one going up is 0, 0. No. So there are 2 possibilities of them having 0. And of course, going down, going down. This is -2. So there's for 0, there's 2 possibilities. There's 1 possibility. So this one is here. This is your up and down, down and up. This is your up and up, and one more down here. We're going down here, and one more here. Okay. Right. Now this is your down and down. See now. Okay. Due to this one split here to 3 parts is due to the neighbor here. Okay. So now this fellow here, these 3 fellows here will split this guy, which is here. How will this split? I mean, 3, there are 3 hydrogens here. So n plus 1, 4. 4 kind of peaks. Why 4? Because each of these hydrogen here, right, can have 3 different kind of spin or energy levels. Why if it's go up, up, and up? Remember? So it's up, 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 and up. Oh, that's +3. That means HO plus 3 of this small little magnitude of magnetic field. Okay? So higher. So here be a bit higher here. Okay. Okay. So okay, which you cannot see under low resolution. What's the second possibility is, well, it can go up and down, isn't it? Okay, so it's up. I'll explain again, up and down. So it's +1, isn't it? Yeah, right, because these two will cancel each other. Or it's up, down, and up. Once again, up, down, and up. Also +1. You know? Or down, up, and up. Okay, down, up, and up. There's only 3. So -1 again. Sorry, +1. How am I talking about? So these 3, right? +1. There are 3 possibilities. So it's 1:3 here. Okay, and the next one, of course, if it's down, is it up, down, down, and up, which is -1. Or down, up, and down, which is -1. Or up, down, and down, which is -1. Also, the 3 possibilities, so 3. And of course, last one is down, down, and down. There's only 1 possibility. So you've seen in 3 parts. 1 here, 2 here, okay, 3 here, and out. Okay, see. So 3 will split it into 4. So n+1 rule. Okay, so this one will not split because oxygen prevents it. See now. So this is called the spin-spin coupling. Now look at it down here. See? Now, yeah. Okay. Okay. Right. So this, as I said, why is it 4? Why HP is 4? Because of the CH3 here. The 3 here. Okay. The 3 here can have 3 different energy states combined together to be felt by the 2 hydrogen here. Okay, right? So 1:3 1:1. Why 3? Because there are 3 possible arrangements. Okay, so that's how this thing happened. Now let's look at how you apply it. Okay, I'm going to go to page this 35, 41. The plan already. Then the plan is going to fail. Okay, see that the amount of splitting tells you about the number of hydrogen attached to the carbon atom or next door carbon, or the term used in Cambridge is called what? Adjacent hydrogen or proton. Remember, adjacent means what? The hydrogen here got 3 covalent bonds. 1, 2, and 3. No. Okay, that means this fellow here will, this fellow here will, this fellow here, okay, will affect this one here. Okay, all right. Okay, they call it subpeaks or clusters. All right. Now let's go here. Now, what information can you get from the NMR spectrum? Now here you get 2, 3, 3. Now, because this one's about 1.3, that means you expect this to be CH3 joined to a C, isn't it? It's not. Why? See here, right? Around this value here, CH3 joined to, of course, here's the carbon. If it's to oxygen, then that means with this one already. It's not. Yeah. So you can see here. So this one will be CH3 joined to a C. Right? Now this one here, first of all, talk about the type first. Okay, now here, 4.2. Now actually, they say that this has a formula of this one here. They will tell you one. This is a formula here. Okay? Formula of this one here. Okay. Okay, now here. So this is the formula. So assume that you know the compound has this molecular formula. Anything with O2, that means it can be either a carboxyl acid or a what? Or an acid. These are common ones. Of course, you can have dicarboxyl acid, whatever, or your diol. Okay, so assuming that you have this one here, normally you'll be given more information, like for example, your mass spectrometer, your infrared spectrum, which can actually know one. Okay, so now let's say if this is the case here. Okay, if this is the case here of ester, all right, ester here can be, let's say, okay, CH3, therefore CH2, carbon, okay, and O here and CH3. You count here 4 hydrogens, 4 carbon, 8, 3 plus 3 plus 8 is it? 2 oxygen, yeah. Or it can be, this is your methyl propanoate, okay? Or it can be CH2, C double bond O, and CHO here, and CH2 here, and CH3 here, right? Right? Or can be H here, C double bond O, and O, and CH2, CH, 2 and CH3. Or last one is isomer. This one now, of course. H here and O, sorry, C here, O, and your O here, and C and CH3, and CH3 and your H. Is that? All can be your carboxylic acid. Let's say from your whatever other information from your mass spectra or UV or IR, you say it's an ester. Okay? So now remember, if this is the case here, I will have here 3 types, 3 peaks, 3 types of peaks. Because 3 chemically equivalent hydrogen. Here's a 3 peaks. Here I got 4 peaks. Here I got these 2 are same. 1, 2, 3 again, 3 peaks. So let's look at this one. How many peaks it got? 3 peaks. See now, 3 peaks. Okay, because it doesn't have the carboxylic acid, which is, let's say, the carboxylic acid down here. See, okay, it's very high. Remember 11? Yeah. So it cannot be carboxylic acid, okay? Because it doesn't have such a high value. It's not. Okay, so it has to be an ester. Now remember. Now you can see that, well, the 1.3, that means it's for CH3, right? That means the 3 here, 3 here. Now this is by itself, see? Right? That means, see, this fellow here has this fellow here, see? Because this is a high resolution, this one can got no adjacent protons. This split and this split, that means that these 2 has got what? Adjacent protons in. Now, very common one. 2 and 3, that means this is a CH3 and a CH2. I'm drawing the reverse. So of course, this 3 will split this one into 4, a quartet. This 2 will split this into a triplet. Yeah? See now? So that's why 3 and 2. Okay? Right. Of course, it's 3 hydrogens, 2. Of course, this 3 will be this one here. Of course, this 2 here will be a CH2. Right? Which is next to a CH3. Okay? Right now. Which means that 1 point something, that means it's this one here. Okay? Now why split into 3? Because of this one and this one here. 2 adjacent hydrogen to these 3 fellows here will split this one here into 3, a triplet. That's not. Okay? Right? Now this is next to this one here. Okay, so these 3 fellows here will split this fellow here into how many? Into 4. See now? See? This is how you know. So you must have this fellow here in your problem or in your solution, right? Which is here. So this is the answer. See? Now just I draw away over here. Okay, here. Okay, right? Now this is just CH3. Sorry. Okay, CH3. So now of course this see got yeah. Okay, yeah. Okay. So cannot be this one here, and cannot be this one here, because this one here, right? We have this is 6, the height of 611 cannot be this one. So this 2. So how do we recognize which one? Very simple. Okay. Now look at the hydrogen here. Okay. Right. Now this one is this hydrogen here. This one here is that C H to a C11O. See now. So CH3 to here is right. CH3. Well, this CH3. Okay. To an oxygen, my dear friend. This is to a carbon. This to oxygen. It's not. To here. This is not. So this hydrogen here is to carbon, oxygen is to carbon. That means this fellow here will be more downfield, isn't it? Will have a high energy level, isn't it? Right now, will be a lot bigger field than this one, isn't it? Right now. So CH3 to O. CH3 to O. Now look at it here. CH3, see now? CH3 to O. Yeah, baby. 3.2 to 4. Right? If the other one, if this one here is 2.2 to 3, right? That means if this one is below 3, it's over 3, isn't it? Right now. So let's say here. What is it? Okay? Well, it's below, isn't it? 2.1. So it's below 3. So below 3 is what? Below 3 should be this one here. See this one here. So CH3, C double bond O, okay? Not next to the oxygen. So So it should be this one here, right? Should be CH3 to C double bond O. Which means what? It should be, which one? It should be this further here, this answer. Okay? Let's see. Correct now. See, yeah, that's right. See, so, yeah. Understand? Okay, so you must see each of this, you must see the splitting, you must see the position, you must see the value, okay, right? So this is the answer. So how you do it, okay, the splitting. Now let's look at other examples. I've got about 50 more minutes to finish. Okay, I'll show you other examples so they can have better grips. So next time we show in, we'll do mass spectrometer and then combine all together, all right? Next one is page 44. Now down here more examples. One more first. Now, you look at this, it's 44. I look at the syllabus. Right, I'll show you what I'm trying to tell you. Okay. You see here they say, down the last part here. See, normally here, I'm going to do this idiot. Okay. Now, here, state the need for deuterated. That means there are no hydrogen. If it's CHCl3 here, this chloroform, the hydrogen will affect the spectrum, isn't it? So there must be no hydrogen in your solvents. So you can use CD, of course, it's deuterium, it's heavy hydrogen here. So describe identification of OH, NH, and also SH, I'll show you, okay? All these three here, the protons of this here, right, can have proton exchange by D2O. Now, what does it mean? It means that if this is your ethanol, okay? Because ethanol here is a bit acidic. Use CH3, CH2, and dodge to O minus up. Yeah. Why acid? Acid means up. Proton donor. That's not. So when this is here, right, the C2H5O can react with DOD, which is D2O, heavy water, to give you C2H5, O and D. Okay? Plus HOD. Right now. So this one here, that means this further here will disappear. The 0.5 to 61 here will disappear. Okay? They will disappear. That means you put this heavy water inside here, the signal will disappear. That means it must be alcohol. It must be amide or amine, or it must be a sulfur hydrogen bond. Now I'll show you what I mean. Okay? Let's go back to the theory first. Page 41. And I show you the example for a partial question. Okay? Right, see here. Sorry. 44. 44. Here, see, right? If you measure the NMR spectrum of alcohol ethanol, add a few drops of deuterium oxide D2O in the solution, allow it to settle down and remeasure the spectrum, the OH peak will disappear. By comparing the two spectra, you can say immediately that which peak is due to OH. Okay, so remember it will disappear. Okay, because it's slightly acidic. Okay, now here, see, you can put the ask for equation. This equation put. Okay, the D will go inside here. Why? Because this further here is the alcohol is a bit acidic. Okay, it will give away the H plus. So the deuterium will move inside here. Okay, right? Whatever here. Now I show you the question that talks about this one here. So you can see how it actually comes out. Page 95. Okay, I'm going to watch 95. 95. All right, now here, the NMR of cysteine. This is the amino acid. I draw it for you here, and H. Okay, CH here, right? So H here is gone down to C, H here, cysteine. Those who have curly hair will have this cysteine. Okay, right? Okay, this H here. Of course, this is C upon O and OH here. See? The NMRs of cysteine show 5 absorbance. That means 5 types of hydrogen, 5 types of equivalent chemical equivalent hydrogen. 1, okay, 2, 3, 4, and 5. Correct? Okay? It means 4 different peaks after shaking the system with a few drops of D2O. That means that D2O will exchange, because proton exchange, okay? Will exchange this one here. I put blue color, okay? Blue color. This one here, let's put a D. This one here to D. This one here to D and to D. Okay? That means these 3 peaks here will disappear. You know, says the NMR spectrum now shows only what? 2 absorbance, E and F, shown here. Very easy. So E, the one peak here, the one peak, 5 absorbance here, right? So there are 5 peaks now. 1, 2, 3, 4, whatever. Okay, 5 peaks now. So the 3 is gone. The 2, for low absorption, 1 peak here will split into 3 and 2. Easy, isn't it? That means this E, right? Okay, E has been caused by F to split into 3. That means F here has got how many halogens? Has got 2 halogens here. That's not okay. Right now. Now E here, F here will split into 2. That means E got how many halogen? 1 halogen. That's not. Yeah, because 1 halogen will split this one here, 1 peak into 2, isn't it? Why? Because this halogen here go up or down. So this one will be up, this one will be down. This 2 halogen here can split into 3, because the 2 halogens here will be up, or up and down, or down and up, or down and down. So it's 1, 3, sorry, 1, 2, 1. See it? See? So it means E must be what? E must be, if it's 1 halogen here, E must be this one here. E must be CH. Right now. Right? F must be F, F isn't it? Right? Split by 3. Right now. Okay? That means it must be it must be 1. Which 1 here? Sorry, what am I talking about? This is, so I got confused also. E is F is F, it will be 2. Okay? F is 2, this is F. Right now, says 2. That's not. Right? Right? So 2 will split this one into 3. It's a E. 1 will split this one into 2. No. Okay? Let's put marking same. Right? This is what here. Okay. State and explain the splitting up patterns of absorbance E and F. Okay? Right now. Okay? Why? Because as I said, now let's see how you answer is splitting patterns, okay? Which is 2 is 3. Okay, this is what year? 15 November. Okay, here we are. Last one. Okay, E is CH3 right now. E is CH, sorry, CH. Okay, E is CH. Yep, CH1. And F is CH2. Yes, not. Okay, now how do you answer about the splitting part? Look at here. Okay, right? E triplet. That means E means adjacent to 2H. See, E is triplet. That means right, E is triplet. Triplet is 1, 2, 1. That means adjacent halogen. How many adjacent halogen I have? Must have 2, isn't it? Right. That means adjacent to how many? That means E is adjacent. E is adjacent to 2 halogens. See now. See answer. Right. Triplet adjacent to halogen. F is duplet, adjacent to 1 halogen. See that? This is how they want you to answer. Okay, so the type of halogen and why the splitting patterns. Is that clear? All right. Now let's look at some more. Okay. Now I'm going to go back to here. I know the time got 7 more minutes or so. Now let's look at different examples. All right. The examples are given in page 44. I think 44, 48. Let's quickly go. 44. All right, here, okay, you can read over here you want to, okay? Now, here better examples, okay, here. Now remember, this is all high resolution, okay? CH3BR, which means, right, there's only one type, so there's no splitting, okay, one type, okay? So it's about, because of BR is very different, so it's down the field here, okay? Quite high, 2 point something, okay? right? TMS is 0 here. Now next one here. All right, now this of course, again, there are 6 hydrogen here, but they are same chemical environment. So again, 1. No splitting. They don't split each other, one. Because same means don't split. Now here there are two kinds of chemically equivalent hydrogen. And draw for you. H here, H here, and H here. C and H here, and Cl here and Cl here. Of course, this hydrogen will be more down here, right? Because of the high electronegativity of your Cl. Yes, no. Okay. This is more shielded. There is a pull out here, so feel more of the shell, more of the cell field in. So it's down here. Okay. Now this is a CH3. Okay. This is your CH. Right. Now these 3 fellows here. This one here will be this hydrogen here. Right. Who is the okay, I put red color. This hydrogen, these 2 hydrogen here will be split by who? The adjacent one, this one and this one. This one here, okay. Right. This is the adjacent hydrogen to this 3. Why? Because 1 bond, 2 bond, 3 bond. Okay. 1 bond, 2 bond, 3 bond. 1 bond, 2 bond, 3. Now, this fellow here can spin up or down, isn't it? That means this fellow here will split this one peak into how many peaks? 2 peaks. Duplet. D-U-O-B-L-E-T. I how to spell duplet. B-L-E-T. Okay. No. It's terrible, Mr. Lai. Anyways. Okay. Duplet. 2. Right. Draw. Red. Okay. Now, then this hydrogen here, this 3 will be its adjacent knot. Okay. That's 1, 2, 3. 1, 2, 3. 1, 2, 3. So these 3 fellows here will be the adjacent. So this fellow here will see these 3 fellows here. And what are the, how many are there? 3. So these 3 fellows will split this into quartets. 4. Why this one will be? Of course, spin up, and spin up. Okay. This one will be, for down is spin up, and spin down, spin up, spin down, and spin up, spin down, spin up, and spin up. Okay. Okay. So here will be spin down, spin down, spin up, spin down, spin up, spin down, spin up, spin down, spin down. Okay, so it's 1, it's 2, 3, it's 3, and of course that one is spin down, spin up, spin up. Okay, right. So this is how you can see it. Okay, now some more examples here again. So this is now the 3 is to 2 pattern. Okay, that means this one here of course must have how many? Because it will affect here now, okay? To 4. Let me see here, 3 hydrogen. Right? Here will affect here. This one will affect this one here, will affect this one here. So this one here is 1 point something here. Well, there are 2, let me split this fellow here. How many? In 3. Okay? Triplet. This one here, 3 fellows will split this one into 4. Quartet. Okay? Right. Some more. Now here, here's quite nice. So of course, this one here will be, I draw it out for you here. All right. A lot of examples, you go and try and talk to yourself, okay? And draw it out so that you can actually understand yourself. Okay? Now, there are of course 3 different types of hydrogen or 3 chemically equivalent hydrogen. One is HA, HB, HB, HC. Okay? So now remember this fellow here, this 3 fellow, who is the adjacent hydrogen? Okay, okay. So put black color since it's black here. Black color. Okay. So this 2 will be adjacent to here, isn't it? Right? That means this 2 will split this 1 into how many? Triplet. Say triplet. Okay. Okay. Now, again, now this 3. Okay, I put green color just to make better this color. This 3, 1, 2, 3 is adjacent to who? To this, the black fellow here. Okay, because 1, 2, 3, 1, 2, 3, 1, 2, 3. No, so now this 3 fellows here will split this 1 fellow into how many? Into quartets, right? 4. Okay, 3 plus 1, is not? Yes. So this fellow will split the black color here, the 4. But This fella here is also adjacent to this one, sir. That's 1, 2, 3, is it? Yeah. 1, 2, 3. So total 3 here and 2 here, 5. So n plus 1. So 6 in. Yes, so 6 lines. Yeah. So this actually belongs to this fella here. Okay, now this fella here, these two fellas here. Okay. Put another color, okay. Maybe brown color. This one here. Okay, how many who are adjacent hydrogen? 1, 2, 3. It means these two. This one cannot. This one cannot. So 1, 2, 3, 4 cannot, is it? Yeah, bromine cannot. So 2 fellas here. 2 fellas here will split this one peak. How many? 3 peaks. See now? 3 peaks here. See? 3 peaks here. So this is the spin-spin coupling. Okay? One more here. So of course, now this one here, you see I've drawn the CH first. Okay, CH, right? And it's OH here. Okay, and of course C is CH3, H and H here, and the CH and H and H here. Okay, so these two fellas here, the 6 fellas here are chemically equivalent here. Yes. Okay, so we get 3 peaks here. 1, 2, and 3. Of course, OH, you can see this singlet won't undergo spinning, but of course it will disappear, right? With the D2O. So now, for these 6 fellas here, right? Who is adjacent hydrogen? 1, 2, 3. This one here. See now, here also 1, 2, 3. That means the 6 fellas here got only 1 fella here to affecting it. So they're going to spin up or spin down. So that means this fellas here will spin into 2. So 2 pair. Okay? Right? Now this fella here, right? Which is here. Will be split by how many? 1, 2, 3. 1, 1, 2, 3. 2, 1, 2, 3. 3, 1, 2, 3. 4, 1, 2, 3. 5, 1, 2, 3, 6. You got 6 adjacent hydrogen. That means 6 plus 1, n plus 1. No, that means 7. See, 7 lines here. Understand? Sun won't be split because of oxygen. Okay? Right? Can Okay, now time's up already. So now, well, the next time we'll do mass spectrometer first, and I'll revise with you infrared, and together it will come out in a beautiful question like here. See now, okay? Now this is your mass spectrometer, mass spec, SPEC, okay? And this is your infrared, okay? Infrared. And together, see now, they come with your what in your NMR, and together make up one question. See now, here will disappear. Yes, now this is famous. 5 is your C6H5. This is your phenol group. Okay, so now together they will form a fantastic question. So we'll do this when we go to the next time. See you. I'll do mass spectrometer. Right, go to theory and revise infrared, and hopefully we can do some of these questions. And then one more session, we'll put it all together in one big chunk, and we will finish your organic chemistry. Okay? All right. So, well, goodbye, and I hope you understand. If you don't understand, please go over the video and draw it out, write it out, explain to your friends, whatever, okay, until you get it. Right? Because actually, you need to practice one to see all this splitting. Of course, low resolution and high resolution. Okay? All right, goodbye. See you next time.